Okay, ladies and gentlemen, for our final and last talk of this year's ComSec track, Attack in the Box. We had a bit of a difficulty with Chrome OS solved now, so take it away.
Hi everyone, can everyone hear me?
Well, we got a solution for that.
All right. Hey,
Does it work?
hello?
It's switched on. Now it works.
Hello? All right. Sorry about the technical difficulties, everyone. My name is Ben Schmidt. I'm CSO at PolySwarm. There you go. All right. Just a little bit about us. We're working on creating a distributed threat intelligence market where people can share files and have them analyzed by a large collection of security experts. Today, I'm not going to be talking too much about that. Instead, I'm going to be talking about security vulnerabilities on the Ethereum network, specifically those written in Solidity. So, what is going to be covered are smart contract vulnerabilities that allowed for someone to steal funds or disable the use of funds. So there's been a couple of large profile hacks of a large amount of money, and there's also been some compromises of smart contracts that led to funds effectively being destroyed on the network. These are all going to be things that have happened in the real world, mistakes people have made, but they instruct, how one would sort of go about looking for vulnerabilities in these sorts of contracts. These have really been exploited in the wild, and we'll be looking through how exactly some of those exploits worked. In general, they're pretty simple conceptually, but one of the issues with smart contracts is they're kind of deceptively simple at times. You think you're doing one thing, and you're actually doing something completely different. So what we're not covering today are vulnerabilities in contracts written in other languages. So Serpent is an older language that's sort of Pythonish and is no longer really used. There have been some interesting vulnerabilities in that, but we're not really going to talk about those today. Viper is a new language that is being developed right now that is going to allow for the application of formal methods to Ethereum smart contracts. Those are still, that language is still kind of in development, and there's not really anything that's deployed that uses it. We're also not going to be covering compiler bugs. There have been a few in Sol-C, the main compiler used to generate EVM code from these contracts. So those are interesting too, but we don't really have time to cover them. And we're definitely not going to be covering vulnerabilities and exploits in exchanges that somehow allowed for people to steal them. Steal funds just because they're not really related to smart contracts and just more traditional security issues. So the first one we're going to talk about is in early November, DevOps 199 commented on Parody's GitHub that he accidentally killed it. People weren't really sure what he meant by that until he pulled up the Etherscan address, and apparently he had managed to lock up $300 million in Ethereum just by sending random kill instructions to contracts on the chain. And it's kind of hard to believe unless you actually go through the conversation, but he was just going around on the networks trying to kill and destroy every contract he came into contact with. For some reason, this was able to take out a bunch of people's multi-signature wallets and lock up a bunch of funds in a way that is essentially unrecoverable even today. So the core of the problem is, and how many people in here have looked at Solidity code before? Anyone? So if you don't know Solidity, it's kind of weird mixture of like JavaScripty syntax plus some C underpinnings that is somehow used to manage all of these funds all over the world. And what a smart contract is essentially doing is it's defining state changes. So everyone is executing this code and agreeing that given these inputs, the chain should change in this certain way. So everyone goes through very systematically and executes some bytecode, and everyone agrees on what the outputs of that contract are. So in this case, solidity is what they were using to describe that state change. And what you're basically looking at here is one of the initialization functions in the parity multisig wallet. The problem is that the parity multisig wallet was a bit over-engineered and separated a lot of their initialization code and shared code out into a library. And it's actually possible to have library contracts on the Ethereum blockchain. So all these different multi-sig wallets were actually calling into this one centralized library. And this function was one of the functions that was exposed. So basically, you can add various modifiers to functions that sort of describe when you can call it, describe constraints on whether or not certain people can call it, and certain times when it can be called, things like that. So in this case, this function was not supposed to be called if the contract had not been initialized yet. In this case, because it was a library, no one had actually initialized the library contract. So whenever you went to go call this, only uninitialized was actually true and allowed you to set yourself as an owner and then immediately kill the contract, which is what DevOps 199 ended up doing. So the actual how that works and why they had separated it out was that in their default function, parity devs basically said, okay, we want to separate out this library code from this wallet code that's specific to whatever thing you're deploying. And they wanted to do that basically to save money, because it costs money to put code onto the Ethereum blockchain. So what they have to allow you to call into some of those library functions is they implemented a default function here. So anytime you send Ether to an address, if you're not explicitly calling a function in that contract, it actually executes this function here. And this is known as the fallback function. So this function basically handles anytime someone sends money to this contract or calls something that isn't actually defined in that contract. So what they're doing here in this code is passing in, so they were unable to find this function, but they can see that a contract function is attempting to be called and pass that on into this library through what's known as delegate call, which is different from a normal call. We'll get to that in a second. So delegate call is defined in the Ethereum yellow paper as almost essentially the same as a call function. However, it actually maintains the same local state of the contract that is currently being executed. So rather than calling into another contract and replacing the message.sender variables and so where the call came from, it actually maintains all the current state of the executing function and only replaces what code is currently executing. What that means is you can create these library functions that you can call into and have them do something on behalf of your current contract without changing any of the state that would normally mess up your inter-contract call. And just sort of a comparison, it's sort of like swapping out the text section and the binary. So, if you dynamically swapped out what code is actually running, but you maintained the actual data and the stack stuff of the currently executing process. So basically that allowed someone to freeze $160 to $300 million, depending on when you valued that. There was no fork to save those funds, so those funds are still locked up indefinitely. The vulnerability was obviously that the library itself wasn't initialized, and someone came in and initialized it, became owner, and used that ownership to suicide it. That's kind of crazy, but because of some of the complexities of the inter-contract operations, it's not necessarily obvious that this sort of thing would be a vulnerability. Now, this vulnerability was actually, vulnerable code was actually introduced in response to the first parody hack, which we will maybe talk about later. So the next bug type that we're going to go into is unhandled reentrant control flow. Now, reentrancy is a problem that is entirely dependent on inter-contract calls. So you have one contract and it calls out to some other contract, and that contract calls back into yours and modifies state internally that you weren't expecting it to modify. Now, what complicates this is in a lot of cases, just sending money to a given address could be equivalent to calling in to that contract. So if you remember earlier, there's fallback functions that you can implement that actually do things whenever you're sent funds, even if there's no function being called, even regardless of what's happening. So if you call something with .call.value, it actually forwards the remaining gas that you're using to execute this contract, and it allows that fallback function to execute arbitrary code that an attacker might specify. So the attacker's contract can then go back into the vulnerable code as many times as it wants to and change various things about the state, which could potentially violate developer expectations. The correct way to do this is actually to use the functions .send or .transfer, which basically prevent you from doing this because they limit the amount of gas to execute the transaction. I suppose I should explain a little bit about what the function of gas internally in Solidity contracts, but the difference between the Ethereum virtual machine and Bitcoin's script language is that the EVM is actually Turing complete. And the way that they actually solve the Turing completeness problem to make sure, that you can't, just arbitrarily execute code indefinitely. The contract will actually terminate executing if you run out of funds to execute that particular contract. So it keeps track of every single execution that you do and every single value that you store to the chain and charges you essentially for that. So if you run out of funds midway through, your transaction is reverted and nothing actually happens. So in this case, if you do .send or .transfer, it only forwards 2300 gas, which is just enough to record the transfer of funds and not enough to actually call back into these vulnerable contracts. So to exploit it, you author a contract, use fallback function, calls back into it, and goes after it. So in the case of the DAO, has anyone heard of the DAO before? So this was one of the first big hacks on the network, and it was a result of smart contract in this thing called a distributed autonomous organization. So what they were trying to do was create this thing where people could propose ideas, and they could basically create new tokens, and then people would eventually get paid back if that particular project made money. In this case, though, unfortunately, they used that same .call.value idiom to send funds to people, which allowed the attacker to actually call back in to get his rewards. And the problem is that the rewards being logged, so the amount that was withdrawn from the contract, was updated after the actual call into the attacker's contract, which allowed them to basically recursively dump funds from this contract. So it was a sort of simpler example than that, and this is taken from TrailofBit's Not So Smart Contracts repository, which is really neat if you guys are interested in some simple examples of how these things work. But as you can see, there's a reentrant contract that basically allows you to withdraw funds from some balance that's recorded on the chain. And unfortunately, it doesn't actually update the balance until after it transfers the funds to those users. So because of that, in this exploit, you can actually call that and then set your fallback function to continuously start dumping. So in this case, it only jumps back into the contract once, but you can potentially do that as many times as long as you have enough gas to continue making that call. So there's another bug, and now coming back to that same parity hack with the library. So the first parity hack, they actually managed to steal only about 30 million, although they could have stolen up to 200 million. Thankfully, some white hats came in and stole a bunch of funds and gave them back to the community. About a couple weeks after that, someone came out and posted that he was responsible for this, and he did it because he had a bad Tinder date. I'm not sure that that's actually what happened, but it's a pretty entertaining read if you haven't seen it. So the problem was that in addition to that delegate call issue that allowed you to call anything in that library, there was also an unprotected function called init wallet that initializes the wallet and sets all the owners of the contract. So correctly, it was supposed to limit the people who could limit withdrawals only if enough people signed off on that given withdrawal, the way a correct multi-signature wallet should. Unfortunately, this init wallet function had no visibility decorator, and in Solidity, one of its weird quirks that programmers might not expect is that if a function is not explicitly stated to be private, it's actually public, which means that anyone on the chain can actually directly call that function. So combining that with the delegate call function in the fallback function in the original contract, you are actually able to call init wallet on any of these contracts, which allowed you to set yourself as the only owner of the contract and then withdraw all the funds. So because it's not public and it does this delegate call, you can see that you should be able to set yourself as an owner. There's a few extra steps in here, but I'm running a little low on time, so I'll gloss over them. But basically the idea is that because you can call in the context of this contract, you can actually set yourself as an owner and withdraw everything. So here's an example of the exploit straight from the blockchain, and it's very, very simple, and you'd almost miss it if you were watching, even if you were watching for it. But so this sort of problem actually happens a lot, where people don't correctly protect their functions. There was one particularly amusing one that was basically a pyramid scheme. They called themselves explicitly a pyramid scheme. They were called Rubixi. Someone really liked this idea and copied their code and renamed it to Dynamic Pyramid and started convincing people on random forums to join their pyramid scheme. The issue with this is whenever they renamed the contract to Dynamic Pyramid, they didn't actually update the constructor in this contract code. Now the problem with that is that the constructor is actually only called during smart contract deployment, and after that the code isn't even stored on the chain, it disappears entirely. For that to happen, however, it has to the constructor to the smart contract actually has to be named the exact same thing as the contract itself, and if it's not, it just becomes a normal public function. So in this case, someone deployed this contract and got a bunch of people to participate and actually didn't initialize their wallets. Someone initialized it and then drained the entire contract. Another interesting one was the King of the Ether Throne, which was another pyramid scheme by another name. Basically, every time someone sent more money to the contract than had ever been sent to it, a portion of that was paid out to the previous winner, and the new winner was installed as the monarch, who would eventually get paid out the next time another sucker put more money into the contract. The problem is that if you don't actually check the result of the send, it can potentially fail, but the contract will continue executing. So what you can do is you can actually prevent, if this send fails, then you may be able to steal funds that were rightfully supposed to go to someone else. So in this example, the current monarch gets replaced, but the outgoing monarch misses out on this fee, and if they had actually checked for the failure, this wouldn't have happened. So checking without that is bad, but sometimes throwing is actually worse. So there's some examples of contracts where people were withdrawing to a bunch of different addresses of previous investors, but if one of the sends fail and the contract throws, actually no one can withdraw any of their funds at all, and people call this griefing. So something that people also have trouble understanding about, smart contract security is this idea that everything you're doing is public, and not only is it public, but sometimes it's public before it even hits the chain. So someone wrote a rock, paper, scissors game where you could bet 1 ETH on a game of rock, paper, scissors. The house takes 1% when there isn't a tie, so it's just a random gambling game. The problem with this is that you could see everyone's moves in the mempool before they were actually committed to the chain. So you could watch all the new transactions being submitted to the network before they actually confirmed, and bet on the correct thing, the correct move, so that you would always win the game. So you see someone do scissors and you throw rock immediately. So there's a bunch of other types of vulnerabilities that are pretty common. So generating random data on the blockchain is actually pretty hard. So one of the most common ways to do it nowadays, because it's so hard, is to actually pull from data sources of people who periodically publish output from random.org to the chain. I don't know how much you trust that, but I don't very much. So there's been some examples of some PRNGs that are not very safe. Some people attempt to use the block hash to do this, but that's only safe up until a point when, if you're managing enough money that malicious miners might actually be interested in the funds you're controlling, then it could not be safe. Integer overflows are still alive and well. You have to check everything to make sure it doesn't underflow or overflow. Unfortunately, Solidity doesn't do anything for you there, so you have to manually pepper your code with things that actually check for those. Race conditions are also a problem, and those can be kind of hard to see as well, because sometimes some of these bugs depend on when various transactions actually hit the chain. So if you can race things and put a much higher transaction fee on top of your transaction and then beat someone else, that can be a problem. I think I'm running a little low on time here, but there's a bunch of really great tools out there that are still under active development. These are pretty new. So Mithril is really cool, trying to do symbolic analysis and things like that on smart contracts. Porosity's under active development. There's also some tools on here that I haven't updated yet, but Trail of Bits has a bunch of analysis tools that are really useful. I recommend checking them out on their GitHub. They have a fuzzer, and they have a nice plugin for Binary Ninja to actually review raw disassembly. And I've got some stuff about how PolySwarm is doing it, but I think I'm a little out of time here. So does anyone have any questions?
Did you look at Ether kittens?
Ether kittens. I bought a couple. I didn't do much of a security analysis on them, other than that they were able to single-handedly DOS the Ethereum network. But